This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, the professor for this class at the University of Texas at Austin. And this is Lecture 53 on lithography with the topic of resist development. As we've already discussed, one of the key ideas of a photoresist is that by exposing it, we change the solubility of that resist in developer. What we haven't really talked about is what we're trying to achieve more specifically. Obviously, we want a region of the resist that's going to be soluble, wash away, and create the spaces, the open areas of our patterns. And we want another region to be insoluble in developer so that the resist remains. But what do we want in the in-between region, at the edge between where the resist is soluble and where it's not? Well, what we'd like is a very sharp distinction between the region that's soluble and the region that's not. We want a sharp edge. We want step functions of photoresist when we're all said and done. To achieve that, we need highly nonlinear development behavior. So let's think about development in this way. The development rate will be defined as the rate at which the thickness of the of the resist changes with time. So development rate is some variable r with units of nanometers per second. In fact, it doesn't. You don't have to think about development going perfectly straight down. Development will always proceed perpendicular to the surface of the resist, whatever surface that might be. If the resist is vertical, then development will be proceeding perpendicular to that vertical resist profile. So whatever shape of resist profile that I have, the development is occurring perpendicular to that, and we can talk about the rate at which the surface of resist moves in nanometers per second. Then the thing that controls the dissolution will be the relative inhibitor concentration, little m. For a DNQ resist, that's going to be the concentration of the DNQ. For a chemically amplified resist, that's going to be the blocking group or the protecting group on the polymer. So for either kind, we'll think about the inhibitor concentration as the species that controls the amount of development. Of course, the inhibitor will change into something else. In the case of a DNQ Novolac resist, the product of the exposure reaction enhances dissolution. But since there's a one-to-one relationship between them, all I need to know is one of those two concentrations. So I'll pick the inhibitor concentration to think about. An inhibitor concentration of 1 means completely unexposed resist. We're thinking of positive resist here. Everything's quite analogous for negative resist. Just this whole curve gets flipped around. But we'll stick to positive resists for our examples. They're the most common, most popular resists used in our industry anyways. So when m equals 1, we have completely unexposed, completely unreacted photoresist. And for a positive resist, that region will have very low development rate. When m equals 0, we have completely exposed, completely reacted photoresist. For the case of a chemically amplified resist, we have completely deprotected polymer, pure polyhydroxystyrene as our results for that example material. That means we get a very high development rate. And one of the things we think about is what's the ratio between the maximum development rate over here and the minimum development rate over here. And that's an important quantity to understand. And the higher that ratio, the better. But even more important than the ratio of the max to the min development rate will be the behavior of the development rate in between those two extremes. For example, maybe it's linear. If the development rate behaved linearly with the relative inhibitor concentration m, we would have a purely linear resist, straight line dissolution rate curve. That is not what we want. What we want is something highly nonlinear. In fact, you can think about the ideal photoresist as being a step function. I can expose and expose and expose, and the resist does not change its solubility until I hit a certain threshold of level of exposure. And then all of a sudden the resist completely washes away. That would be an ideal photoresist. Well, we can't achieve that. We cannot achieve that. But we can achieve something approaching that. And that's what we're going to look at here. We want a highly nonlinear resist. How do we get a highly nonlinear resist? I'll explain. Suppose I have a photoresist that I'll make in a cartoon way look something like this. So the red squiggly lines here represent the polymer. I'll think of a chemically amplified resist as my example. And then on this polymer I have certain blocked sites given by these M. So this example here I show one polymer with 4 block sites. Now there might be 2, there might be 4. Most modern resists have much more than this, maybe 8 or 10 block sites per polymer. But I'll use 4 in my example. So I'll take this resist and I'll stick it in a sea of developer. What will happen? Well, if I have not caused any deprotection of the resist, those black sites will inhibit the dissolution of the resin. The developer molecules will look at this blocked polymer and say, no thanks. This is not going to go into solution. We're going to sit there and nothing's going to happen. Or at least there will be very, very slow dissolution. So maybe by some alternate mechanism, I get a very, very minor amount of dissolution that occurs. We'll call that the minimum dissolution rate, R-min, but it's very small. Now, let's begin the process of exposure and deprotection. So I expose, I generate an acid, the acid moves along, and let's suppose it deprotects this particular group. So I'll put a little asterisk, M star, to represent in this cartoon this particular site has been deprotected. Now a deprotected site is acidic, and the developer likes that site. So the developer will attack right here at that site and try to dissolve the polymer. Unfortunately, that polymer has 3 other protected sites that do not like that developer at all and inhibit the dissolution of the resin. So what happens? Well, I'm sorry, that one lonely deprotected site is not enough to get the developer to go in, the polymer to go into solution. The 3 protected sites win out, they hold it back, and we do not get dissolution. Okay? Well, suppose I exposed a little more and I reacted a little bit more, and an acid found its way to this site and caused a deprotection event to occur. Now I've got 2 deprotected sites wanting to pull that polymer into solution, and 2 protected sites trying to keep it behind. The developer looks at that situation and, well, I'm sorry again, but the protected sites win out, and the 2 deprotected sites aren't enough to pull it into solution. Okay, let's keep exposing. Let's keep deprotecting. So I deprotect a little bit longer, and lo and behold, this site becomes deprotected. Now I've got 3 sites that are deprotected trying to pull that molecule into solution, and 1 site trying to hold it back. Well, you see that we've got a tug of war going on here. The deprotected sites are pulling to get that molecule to go into solution. The protected sites trying to hold it back. At some point in time, the deprotected sites will win out. There'll be some number of deprotection events that work in concert to cause that one resin molecule to go into solution. That number, we'll give it a name in a little bit, but that number is going to be key. The number of deprotection events that have to occur to cause one polymer resin to go into solution. All right, with that in mind, let's develop more formally our mechanism. We'll have a multi-stage mechanism. In fact, it'll be familiar to you if you looked at the Deal-Grove model of oxidation and our simple model for CVD reaction, it's going to be very similar. We'll begin with diffusion of the developer from the bulk to the resist surface, followed by reaction at the resist surface. Then we'll have diffusion of the dissolved resist into the developer. But I'll assume that the reaction at the resist surface is the rate limiting step, so that the diffusion of dissolved resist into the developer no longer, won't have to matter at all. And we'll focus only on these first two steps. As we said, the reaction at the resist surface will be determined by the number of exposure events or amplification events required to trigger one dissolution event. That number, n, maybe it's 3, maybe it's 5, I'll call the dissolution selectivity parameter. It'll turn out to be the key parameter in our development model. So let's look at these two steps. First, diffusion of the developer to the resist surface. Fick's first law of diffusion can be approximated as a difference equation, just as we've done several times before. Therefore, the rate of diffusion of fresh developer to the surface will be proportional to the concentration difference. Here's the bulk developer D, and D sub S is the surface concentration of developer. K sub D will be a rate constant mass transport coefficient for this rate. Then we'll have a reaction at the resist surface. We'll assume that a developer molecule interacts with n deprotected sites. So I'll let P be the concentration of deprotected sites, or the concentration of reaction product for the D and Q resist. And since n deprotection events have to work together to cause that resin molecule to go into solution, we see that the reaction rate will be proportional to that concentration to the nth power. This is the reaction order of our reaction. And we'll assume that we quickly reach a steady state between these two reactions, diffusion of fresh developer and reaction of the developer at the surface of the photoresist. Setting these two equal to each other gives us the steady state dissolution rate, and we can solve for our one unknown parameter, which is the developer concentration at the surface of the resist. We solve for that, eliminate it from the equation, and the result is our steady state development rate R. We can see that rate as a function of the rate constants and other parameters, but it's easier to couple or lump together various constants into more useful terms. And there will be, in fact, 4 constants required to describe the dissolution rate. First, there's Rmax, the maximum development rate, the development rate that occurs when I've completely exposed or completely deprotected the polymer. Rmin, the minimum development rate, I've actually just added this on at the end. I add this on at the end because I assume that there's some background minimum development rate that occurs independent of the mechanism we just mentioned, and this is an add-on, an added very, very low rate that happens. Then we have our dissolution selectivity parameter N, which is the number of deprotection events that work together to cause one resin molecule to go into solution. And A is a simplifying constant. The simplifying constant A is a function of N, but also a function of our 4th parameter, M threshold. This is the threshold inhibitor concentration. This model, by the way, has been called the MAC development model. I can try to be not be vain and refer to it by my own name, but unfortunately, if you ever talk to anybody else, they won't know what you're talking about unless you refer to it with this name, because that's how it's discussed in the literature. I came up with this model many years ago, and we'll call it the MAC model. So we have 4 parameters. 3 of them are fairly easy to understand. Rmax and Rmin, very easy to understand. N, we'll see its behavior in a little bit more detail. But let's look at this 4th parameter, the threshold inhibitor concentration. What does it mean? Well, the definition of the threshold inhibitor concentration is the value of m at which the second derivative of development rate versus m is equal to 0. Now, does that sound like a very intuitive definition? Well, actually it is when you think about it and if you understand what the second derivative means. So here's our development rate curve. Development rate versus m. M is the inhibitor concentration. Remember that 1 means completely unexposed or unreacted resist. 0 means completely exposed, completely deprotected polymer. And where is the second derivative of this curve equal to 0? It's called the inflection point. The point at which the curvature changes from cupping down to cupping up. So here it's cupping down, here it's cupping up. It's also the point at which the slope reaches its maximum. So the maximum slope of this curve. And it represents, as the name implies, a threshold value of the inhibitor concentration. At concentrations higher than the threshold, we have very low dissolution rates. At concentrations less than the threshold concentration, we have very high development rates. And the threshold concentration represents the transition between those two regions. So the transition from very low development rate to very high development rate occurs at the threshold inhibitor concentration. So in fact, it is an intuitive definition once you think about it. The other important parameter is the dissolution selectivity parameter n. So here in this graph where I varied n, we show 4 different curves. You can get a feeling for all 4 parameters. Rmax is very simply this maximum value that you get, highest development rate. Rmin is way down here, the minimum development rate. M threshold is where the slope reaches its maximum, and I make the transition from low to high development rate. And N, the dissolution selectivity parameter, says how steep this transition occurs. In other words, do I have a linear resist or a highly nonlinear resist? N is a measure of how nonlinear that photoresist is. So what do you think is going to happen if N goes to infinity? I'll bet just by looking at this trend, you'll guess that as N goes to infinity, this curve becomes a step function, a perfect step function with the transition at the threshold concentration, inhibitor concentration. So, by making N larger and larger, we approach the ideal threshold resist that we said earlier was what we were trying to achieve. Getting N to be large, well, that's the real key. That's the real thing we're trying to get at. And this is where resist designers have their work cut out for them. Obviously, by the definition, you can see what's involved. We have to increase the number of blocking sites per polymer so that the number of deblocking events required to get that polymer to go into solution can be higher. One last thing. While describing the entire development rate curve is valuable, there is one region of this curve that is the most important, and that's this knee region. The knee region is the region shown here where I make a transition from very low to much higher development rates. Obviously the threshold is what we call the transition point, but the knee is even more important because it represents what's going on at the edge of development when I'm done developing, at the edge of the photoresist profile when I'm done. When I'm done, I'm going to make a feature, a resist line that has reasonably vertical edges. And the region on one side is going to be highly soluble and all the resist will dissolve away. But right at that edge, the development rate must be pretty darn low, or else the resist wouldn't remain. So all of this part of the dissolution rate corresponds to the portion of the resist that's going to dissolve away. But down here at the knee is where I'm making that transition, where the transition matches the edge of the photoresist feature. Now, if you look at the equation for the Mac development model and consider the case where the value of m is bigger than the threshold concentration, you'll find that the development rate will be proportional to 1 minus m to the nth power. In other words, this is an nth order polynomial, n power function going on right here. And it's that high value of n that that gives us the nonlinear response near the final resist edge where we want it to be highly nonlinear. A linear region is not very important. Well, that's this region. It's quite linear here. It's the nonlinear region that we want, and this is the nonlinear region at the knee of the development rate curve. All right, let's look at what we've learned. As always, you should be able to quickly and easily answer these questions. If not, you need to go back and review the material again. What are the 3 steps in the Mac kinetic development model used here? What development parameter controls the performance of the resist? That is, of the 4 parameters we discussed in that model, which one is the most important? What is the physical meaning of the dissolution selectivity parameter n? And finally, what is the development knee and why is it important? Well, next time we're going to talk a little bit more about development, but from a slightly different perspective. We'll look at another parameter that people use to describe the quality of the photoresist in the photoresist development process, something called resist contrast. Till then.